Hello all, welcome back. Today we will be continuing with our nozzle characteristics. So previously what we have studied is basically your over as well as under expanded nozzles, in what way they will be performing and in what way the fluid flow will be varying. Now coming to our, which is the influence of chamber geometry. Now as we know, the pressure inside a chamber, that is particularly a combustion chamber, is predominantly the core function or a core component through which your exit pressure, particularly or the P2, that is the pressure at the end of a nozzle exit, as well as defines the total optimum condition for your nozzle. Now coming to the chamber geometry, understanding this first primary term, that is P1, understanding that what it gives is basically when a chamber particularly has a cross section that is about 4 times larger, right? 4 times larger than the throat area, also called as A1 to the AT, which is greater than 4, right? Then the chamber velocity, that is V1, may be neglected. But however, in some space or weight constraints, for particularly liquid propellant engines often require smaller thrust chamber areas, and for solid propellant motors, grain design considerations may lead to small voids volumes as well as the perforations or port areas. Now in these cases, particularly the V1s, particularly the chamber velocity is contributed to performance can no longer be neglected, but the gases in the chamber expand as the heat is being added. The energy that is expended in accelerating these expanded gases within the chamber will also cause a pressure drop, and the processes in the chamber can all be adiabatic, that is there is no heat transfer, but it's not isentropic. The losses are a maximum when the chamber diameter, that is the diameter of the combustion chamber, equals to the throat diameter, which means there is no converging nozzle section. That is, if this is my nozzle, this is my combustion chamber, throat, diverging section. Now this type of condition or this type of rocket motor is called throatless rocket motor, and it is found in a few tactical booster applications where the premium on minimum inert mass as well as the length. Now here the flight performance improvements due to the inert mass saves supposedly outweighed the nozzle performance loss of a throatless motor, because the significant pressure that drops within the narrow chambers as well as the chamber pressures are lower at the nozzle entrance than they would be at larger A1 to AT, and this causes a small loss in thrust as well as the specific impulse. Now let us understand the different type of nozzle configuration that we can keep or undergo to understand the nozzles better. Now the nozzles as well as the chambers are typically circular in cross section, and they must have a converging section, a throat, or a minimum cross section as well as a diverging section. Now a converging section is a shape between the chamber, particularly combustion chamber, and throat, but it doesn't affect nozzle performance. In a subsonic flow, can easily turn into a very low pressure drop and almost given any radius, cone angle as well as the wall contour curve or the nozzle inlet shape is satisfactory. And a few altitude control thrust chambers have had their nozzle turn at 90 degrees from the combustion chamber axis without measurable performance loss. The throat, right? The throat contour itself is not very critical to performance, and any smooth curved shape is usually acceptable. Since the pressure gradients are high in these two regions, the flow will always adhere to the walls. It means the flow will always stick to the walls. In general, the wall surfaces throughout the nozzle should be smooth and reflective to minimize the friction, radiation absorption, convective heat transfer, which is enhanced by surface roughness. Gaps, holes, sharp edges, or protrusions must be avoided. Now, these are the different types, particularly, these are the simplified diagrams of generic nozzle configuration and their flow effects. Right? We will discuss this in order to understand better. First, let us understand first three, particularly the cone. Right? These three are my what basically a bell shaped nozzles, whereas other are modifications of the same. First, we will discuss these three. Now, what happens in this is basically, if I consider my first, we'll understand linearly, that is from shape, flow, and completely. So, first case, we will understand the length, right? Now, in this case, what happens, as it's CD nozzle, the small area that is till here to the here is my convergent section, right? And my throat and my divergent. Now, during this, what happens, the wall, right? The wall is symmetric as well as inclined by certain angle, that is 15 degrees. Now, what happens in this case is basically the divergent section of the wall is flat, right? Not in shape of curve or parabolic or anything else. Now, coming to same thing for contoured or bell full length. If I consider the same nozzle, bell type nozzle, what happens? I can put some curvature onto the walls along the same distance, right? Now, if I am putting this curvature, what happens? The flow that is being sent out, particularly through the divergent section under supersonic velocity, will get attached to the wall, right? So that will be acting as a guide way which directs the flow. Now, similarly, another one is nothing but contoured or a bell shape, but it has been shortened, right? Based on our requirement, based on our design, we can shorten the bell nozzle. Now, coming to the flow with an under expansion at altitude. What do you mean by under expansion? Means the pressure that is being inside, particularly pressure 3, the P2 that is being getting at the exit, and PA that is outside is under expanded. What do you mean by under expansion? Where P2 is greater and pressure of atmospheric pressure is greater and pressure of the chamber, particularly the exhaust gases, is less. At that time, what happens? The boundaries, right? The boundaries tends to push further out. For example, let me just say, at an altitude, what happens? The pressure of atmosphere is less, the pressure of gases, particularly pressure of increases. So, along the curve, what happens? It tends to flow as well as it tends to push itself out as soon as it passes through the edge of the nozzle, right? The same thing happens in case of my other two types of bell nozzles, right? These tend to push out further as the altitude increases. Now coming to my sea level, what happens? Initially during start as well as stop, the pressure at inside is less and pressure at out, particular atmosphere is more, during which they tend to push in. Right? Now, as it is a cone angle, particularly straight walled edge, what happens? The flow separation will occur before the beginning of the before the end of the nozzle itself. Whereas if you are considering for any curvature part, right, particularly a bell-shaped divergent nozzle, at the time the flow will not get separated, but it gets compressed while coming out. Right? The same thing. Now, coming to the mass flow. What happens? The mass flow, as the altitude changes, as well as the sea level changes, these are your values, or these are your parts through which the mass flow varies, but the mass flow distribution happens at an exit or the tip. As you are having a straight edge, right? The straight edge nozzle, which is nozzle 1, what you'll be having? There will be a small variation in mass flow rates at the tip, right? At the exit or at the tip of the nozzle with respect to the areas where it is working. Now, coming to other, if you are having a bell type of nozzle, right, particularly the divergent section, at the time the output mass flow or the mass flow distribution along the nozzle edge or the nozzle exit remains same. Now, a small modification out of this is our next, also called as plug or aerospike nozzle. Now, in this there are separate variations, which is either complete length or truncated. Right? Now, in this what happens is basically, if the same nozzle, right, if the same nozzle is being cut into half and mirrored along the other side, right, what will be getting? We'll be getting an aerospike geometry. Right? Now, in this what happens? You, instead of sending the flow in a complete nozzle set, what you're doing, you're redirecting the flow onto the wall of an aerospike. Right? Onto the wall of an aerospike. Now, during this what happens? Basically, as the in-flight progress, as the flow gets pushed out or pushed onto the wall of the aerospike, the flow is coming out, as well as due to the lesser pressure, atmospheric pressure, these tends to move out of the main flow, right? The expansion waves. Now, the same thing if you are putting for the sea level, at the time as the pressure is more, these tends to stick together or maintain a nearby or close proximity till the tip of the aerospike engine. Now, during this what happens? The mass flow rate will be constant till, or will be decreasing at the tip of the aerospike engine. Now, considering the same with a truncated one, what happens in the is basically we will be cutting the length through which the gas is supposed to travel onto a surface, so that you will be creating a recirculatory zones, right? A recirculatory region. And what happens under this recirculatory region is basically, as soon as the flow gets out, it will be having some amount of time to rectify itself. If you're using it in the same under in-flight conditions, the same thing that we have discussed earlier, particularly to aerospike full length engine, that the expansion, right, the boundaries gets diffused and the expansion waves are formed right after the exit of the bell type of nozzle, particularly in aerospike engines. Now, similarly, if you are cutting it off, particularly truncated one, what you are getting along with the recirculatory zone, right, you will be getting the flow, particularly under sea level. Now, for this, what will be the mass flow rate? The mass flow rate will be a maximum at both the sides, right, at both the sides of the aerospike engine, but there will be nil or null or void of mass flow rate that happens at the recirculatory zone. Now, a small change. What if we try to combine this both? Right? What if we try to create a deflection? We expand as well as deflect both the gases at a single time. At the time, we'll just combine these two. What happens? A bell type of nozzle with a small deflector plate, such that whatever the gases you are getting to are getting pushed towards the wall, and a small recirculatory zone is being formed in center. Now, at an altitude, what happens? As the gases are getting deflected, there is the formation of recirculatory region that is known for us. Now, what happens to this? The gas tends to push out, right, as well as it tends to diffuse out, creating an expansion wave. Now, coming to this particularly, if you are creating the same thing for a sea level operation, what happens? There will be a large amount of area for recirculatory zone, right, where there is no amount of thrust or the rocket thrust that is being generated added to the rocket velocity. Only the whatever the gases that is being passed through or aligned to the wall gets included. Now, considering this, what happens? You will be having as a sea level mass flow as well as altitude. What happens under sea level? Right, as the mass flow at the exit plane, if you are considering, there is some initial mass flow at the end, whereas as the plane or the sampling plane passes through the recirculatory zone, you will not be having mass flow particularly. So this mass flow gets in a negative form such that the air from the outside gets in, right? Again, at the end, you are having another intake of mass flow rate again decreasing. Now, coming to, if you are considering for a particular altitude, right, considering the same engine is working under a certain altitude, what happens during this is basically the recirculatory zone gets shortened up compared to your sea level. It gets shortened up, so at the end or at the nozzle exit plane, you will be having a constant mass flow rate, right? Now, coming to this, a small graph which shows comparison of several types of nozzles based on the area ratios to the nozzle length. Now, ideally, a nozzle long bell shape, particularly, right? If I am considering this as an ideal long nozzle, what happens? From the combustion chamber, the gas is supposed to converge, particularly in the conversion section of a nozzle. Then at the throat, the maximum compression, particularly the mass flow rate, unity mass flow. Then the flow gets out following the nozzle wall area, such that it diverts, giving me the maximum flow value. Right, that will be my long nozzles. Now, compared to what we have discussed earlier, is the 4. Right, based on the nozzle area, particularly the nozzle area ratio and the length to diametrical ratio, what happens? The 15-degree conical nozzle that we have discussed earlier is given. This will be the performance graph for that. Similarly, for a nozzle shortened or 4 conical nozzles or a truncated aerospike, this gives you what? Basically, a small comparison to understand with respect to the ideal condition of a nozzle to your physical form. Now, the objective for any good nozzle configuration are to maintain the highest practical and is minimizing the inert nozzle mass as well as conserving length. Shorter nozzles can reduce vehicle length, vehicle structure as well as vehicle inert mass, right? Any nozzle whatever the length might it be, right? The length of nozzle, whatever you are determining, is supposed to act or impact till the time. Right? So later on, as the length decreases, right, the performance of the vehicle also decreases, as well as the vehicle structure and vehicle unit mass. If the length increases, proportionately structure as well as unit mass gets changed. Now, if we are carrying a nozzle of higher dimension, particularly right, higher dimension, then what we are supposed to do? We are supposed to make sure that the whatever the dimensional length, particularly the L by D ratio we are taking, we are considering, that has to be fulfilled, right? That has to be fulfilled during the operation of the nozzle, without which it's not supposed to be considered. Now, coming to our main concept, that is the cone or a bell-shaped nozzles. The conical nozzle is one of the oldest, perhaps the simplest configuration that is available, because it's relatively easy to fabricate, as well as it is still used in many small nozzles. Theoretical correction factor of lambda must be applied to the nozzle exit momentum in any ideal rocket propulsion system using conical nozzle. The factor is the ratio between the momentum of the gases that are being exhausting with finite nozzle angle, that is 2 alpha, where alpha is my half cone angle, and the momentum of the ideal nozzle with all the gases flowing in the axial direction. That gives us the correction factor. Now, for any ideal rockets, the correction factor is 1. And for a rocket with a nozzle with the divergence cone angle of 30 degrees, it means an half angle alpha of 15 degrees, as we have discussed earlier, the exit momentum, therefore the axial exhaust velocity, will be 98.3% of the velocity calculated. That the correction factor lambda only applies for the first term, that is the momentum thrust, not the pressure thrust. The half angle value, that is 15 degree, has become an unofficial standard for reference for comparison correction factors or energy losses or lengths from different diverging conical nozzle contours. A small nozzle divergence angle may allow most of the momentum to remain axial, as well as thus produce the high specific impulse, but result in long nozzles introducing performance penalties in the rocket propulsion system, as well as the vehicular mass amounting to some minor losses. The larger divergence angles such as give shorter, lightweight designs, but their performance may be acceptably low. Depending on the specific application and the flight path, there is an optimal nozzle divergence, typically between 12 to 18 degree as a half angle. The bell-shaped or contour nozzles are possibly the most nozzle shapes used today. They have a high angle expansion section that is 20 to 50 degrees immediately downstream of the nozzle throat, followed by a gradual reversal of nozzle contour slope, so that the nozzle exit at the divergence angle is small, usually less than a 10 degree half angle. Now, it is possible to have a large divergence angles immediately behind the throat, that is from 20 degrees to 50 degrees. Let me consider this as my throat. Nozzle exit. Right, this angle, sorry, not theta, it is alpha, is my half angle. Now, right after the throat, few nozzles, particularly according to our design, the angles can be varied from 20 to 50 degrees. Because of the high relative local pressures and the large pressure gradients and rapid expansions of the working fluid which do not allow the separation of the region unless there are any discontinuities in the nozzle contours. Gas expansion in a supersonic bell nozzle is more efficient than a simple straight cones of a similar area ratio and length because wall contours are designed to be minimizing losses. Changing the direction, particularly under supersonic flows with an expanding wall geometry, requires expansion waves, and these occur thin regions within the flow where the flow velocity increases as it slightly changes its direction, where the pressure and temperature drop, and these wave surfaces are at oblique angles to the flow, and beyond the throat, the gases cross a series of expansion waves, which essentially no loss of energy. In a bell-shaped configuration, expansion occurs internally in the flow between the throat as well as the inflection location I. Here, the area is steadily increasing like a flare in a trumpet, right, in this form, right, where the contour angle, that is theta I, is the maximum at the inflection location. Between the inflection point I as well as the nozzle exit E, the flow area increases at a diminishing rate. The wall contour is different as well as the rate of change in cross-section area per unit length is decreasing. One purpose of the last nozzle segment is to reduce the nozzle exit angle, that is theta E, and thus reducing the flow divergent losses as the gas leaves the nozzle exit plane. The angle at the exit theta I is small, usually less than 10 degrees, and the difference between both, that is the incident angle as well as the nozzle exit angle, is called a turn back angle, that is at the end. Right. Now, as the gas flow is turned into an opposite direction between points I and E, the oblique compression waves occur, and these compression waves are thin surfaces where the flow undergoes a mild shock. As it turns back, its velocity is slightly reduced. Each of these multiple compression waves will cause a small energy loss. The length of a bell nozzle is usually given as fractions of length of the reference conical nozzle with a 15-degree half angle, and an 80% bell nozzle has a length distance between throat plane as well as an exit plane, that is 20% shorter than a comparable 15-degree cone of small area ratio. Now let us understand a sketch that shows a comparison of nozzle inner diverging wall surfaces from a 15-degree conical nozzle, an 80% length bell nozzle and a 60% length bell nozzle, all with an area ratio of 25, and these lengths are expressed as multiples of RT, that is the throat radius. Now let us consider this is my throat region, particularly in the nozzle throat, and this is my location of inflection. For a 15 degrees half angle, what happens? Maintaining my same area ratio, this will be my total length that I am getting, right, from throat to nozzle exit. Now what happens if I change my bell angle or the incidence angle by some degree more? What happens if I am putting my 60% of the length as 60% length bell nozzle with the same area ratio? What happens? The dotted line that is being shown here will be the final nozzle, right? Final supersonic nozzle. If I am putting up for my 80% at the time, it changes its section. Now in this case, what happens? The length, right? The length from my cone gets reduced to either 60 or 80% of the overall length. That defines my incidence angle. right? And the angle between these two particularly is called the nozzle exit angle. So what you are able to understand is as the length, right? As the length of the cone decreases, right, the incidence angle is also increasing, as well as the exhaust angle, right? The exit angle or exit angle gets also increased. So as the length is at a proportion, let's say of 80%, what happens? The incidence angle, so the exhaust exit angle gets decreased from 11 to 8.5 degrees centigrade, as well as keeping my incidence angle as a constant, because we are maintaining the area ratios. Now, the length of the cone can also be represented in terms of half angle, that is R2 to RT divided by tan alpha, where alpha is my half cone angle, RT is my radius of throat, and R2 is my radius at nozzle exit, right? Now, what it shows basically a set of curves which shows an initial angle as well as an exit angle for bell nozzles as a function of nozzle area ratio as well as the percentage of length. Now, what will be my theta I as well as theta I? Now, for expansion ratio, as the expansion ratio increases, we can see that the angle decreases in case of my final angle, whereas my initial angle gets increased. Now, for different amount of lengths, right? For different amount of lengths, what I can see, although there is an initial amount of same angle, that is during stop operation, and as it switches on, as the rocket motor switches on, the angle, initial angle to your final angle varies, right? Varies, it means decreases. The initial angle gets increases as the expansion rate increases. Similarly, the final angle gets decreases as the expansion ratio increases. Now, considering the same, the bot curves, which shows the nozzle losses in terms of a correctional factor, that is lambda, right? Percentage of length of a 15-degree half angle conical nozzle with the same area as a bell nozzle. For a conical nozzle with different half angles and the nozzle correction factor, for a 15-degree point, that is the 100%, this we are having. For different bell nozzles with different area ratios or expansion ratios, these will be my correction factors that we are supposed to consider. Now, the top part of the figure, that is this one, shows a parabolic contour that is tangent to the inflection point as well as has an exit angle of theta I at point E. Now, that is the length L has to be corrected for the curve Ti. And these conditions allow a parabola to be determined whether a simple geometric analysis or from a drawing. Now, the throat approach radius is 1.5 of times of RT, that is radius of throat, and the throat expansion radius is 0.4 RT were used. If somewhat different radii have been used, the results would have been slightly different, and the middle set of curves, that is this one, would be gives us the relation between the length, area ratio as well as the two angles of the bell contour. The bottom set of curves, particularly this one with the correction factor, gives the correction factors equivalent to the lambda factor for the conical nozzles, which are to be applied to thrust coefficient or the exhaust velocity, provided that the nozzles are optimized or operated under optimum expansion, that is P2 equals to P3 or P ambient. Now, For solid propellant rocket motors, exhausts containing small solid particles in the gases, usually the aluminum oxide, or for an exhaust of certain general liquid propellants, solid particles impinge against the nozzle wall and is reversing curvature sections between I as well as E. While the gas can be turned by an oblique waves to have less divergence, any particles, particularly the larger particles, will tend to move in a straight line and hits the wall at high velocities. The resulting abrasion and erosion of the nozzle wall can be severe, especially when a commonly used ablative as well as graphite materials. This abrasion, particularly by hot particles, increases with turn back angle only when the turn back angle is and thus also the inflection angle are reduced. Such erosion can become acceptable. Typically, solid motors flying today, right, will have values of inflection angles between 20 to 26 degrees and a turn back angle of 10 to 15 degrees with different wall contours in their divergent section. And in comparison, current liquid engines without entrailed particles have inflection angles between 27 to 50 degrees and a turn back angles of 15 to 30 degrees. Therefore, the performance enhancements resulting from the bell-shaped nozzles with a high correctional factors values and somewhat lower in solid rocket motors with solid particles in the exhaust. An ideal, which means a minimal loss through oblique waves bell-shaped nozzle, is relatively long, equivalent to the conical nozzle of perhaps 10 to 12 degrees. Because the long nozzles are heavy, in applications where the vehicle mass is critical, somewhat shortened bell nozzles are preferred to be used. Now, considering the next type of nozzles, that is two-step nozzles, that can also be reiterated as two-position nozzles, means with the different expansion ratio area sections, which can give the better performance than our conventional bell nozzles, which having a single fixed area ratio. Now, lower the area ratio, particularly epsilon equal to 6, performs the best at low altitudes, as well as the higher area ratio nozzle performs best at higher altitudes. Now, if the two nozzles could somehow be mechanically combined, the resulting two-position nozzle could perform closer to a nozzle that adjusts continuously to the optimum area ratio that is shown by a thin dashed curve. When integrated over a flight time, the extra performance has noticeably pay off for high velocity missions such as Earth orbit injection or deep space missions. Several bell-shaped nozzle concepts have evolved that achieve maximum performance more than a single altitude. A figure that will be showing us further has three different two-step nozzle concepts having an initial low area that is A2 by AT for an operation at near Earth surface and larger second area ratio that improves the performance at high altitudes during the flight. Another section for those, let me just complete this. Right, two-step nozzles. Right. Before starting that, let me just cover this extendable nozzles. Now, what I mean by extendable nozzle is relatively common for top stages of multi-stage vehicles. Now, what is a multi-stage vehicle? As we discussed earlier, we are keeping multiple rockets one above the other till the desired efficiency or creating an optimum rocket is achieved. Now, its nozzle extension particularly is moved in an operating position after only when the lower stage has finished working and has dropped off. These propulsion systems only operate in space with nozzle extended. The extendable nozzle, which require additional sources of power to move themselves, such as actuators, a power supply mechanism for moving the extension into position during flight, as well as the fastening and sealing devices. They have successfully flown in several rocket motor nozzles as well as liquid engine applications where they are deployed prior to ignition. But there are key concerns which are reliable rugged mechanisms to move the extension into position and a hot gas seal between the nozzle sections and extra weights are involved. its principal merit is the short nozzle length while stored during the operation of the lower stages, which reduces the overall length of the rocket as well as its inert mass. There have been versions of the same concept considering 3 nozzle segments. First one is my droppable insert, which is shown in figure. Let me just write. Now, what happens under this is basically first an extendable nozzle with 2 segments. Right? What happens? This is my primary chamber, right? Where this is my chamber, my first nozzle exit segment, and this will be my second. Initially, there will be a short nozzle that is being kept, right? And this will be my second nozzle part that is being stored while under stowage until unless the rocket gets to a certain altitude. Now, after it, what happens? It gets deployed, or certain mechanisms are employed to reposition the second nozzle at the end of my first nozzle to extend the length, right? To extend the length. Now, based on this extension, what happens? The area ratio, particularly the epsilon is being changed, as well as the length of the nozzle is being also extended. Now, coming to others is basically my droppable insert mechanisms. Droppable insert, that is the mechanism for holding, moving or releasing the insert. Now, having not shown in the picture, if this is my insert and this is my chamber, right? As the same thing, right? As during in-flight, what happens? This insert gets extended out, forming the end of the bell nozzle. Avoids any moving mechanism as well as gases, but has a potential stagnation problem at the joint of 2 segments. The dual bell nozzle uses 2 shortened bell nozzles combined with one with a ring-shaped bump or an inflection point between them. This, right? Dual bell nozzle is nothing but till this point it will be a single CD nozzle, right? As soon as what we are creating a small protrusion or a contour or hump that compresses or acts as a secondary throat. Right? That acts as a secondary throat, which again pushes the gases on a much higher speeds. Right? This will be my primary, that will be my secondary. And what are these? Basically, during ascent, it functions as the lower area ratio, and with the flow separation occurring at the bump, and as altitude increases, the flow expands further and attaches itself downstream at this inflection point and filling the full nozzle exit section and operating with the higher area ratio for higher performance. There is a small performance penalty for a contour with a circular bump. There are some concerns about heat transfer as well, and to date there has been a little flight experience with this concept. Now, what happens if you are using multiple nozzles? Right? Whenever possible, reducing nozzle length by replacing a single large nozzle with a cluster of smaller nozzles, particularly on a liquid engines or a solid rocket motor units, will reduce the overall vehicle length and often the vehicular structure as well as the inert mass. Let us understand a bit. If this is my single bell nozzle, and instead of this, what if I use multiples of shorter nozzles which combinedly give me the same one? What happens? The length of my vehicle decreases as well as the vehicular structure as well as inert mass might increase a bit, but comparatively the length of my rocket decreases. Now, quadruple thrust chambers means for the thrust chambers, particularly 4 times, 4 sets of thrust chambers are arranged and used effectively in several US as well as many large Russian space launch vehicles as well as missiles. Now, the nozzle length of such a cluster can also be about 30% shorter than a single nozzle, but of an equivalent larger thrust chamber. But the vehicular diameter of the cluster nozzle exit location needs to be somewhat larger because the vehicle drag can somewhat be higher, and in addition, the engine complexity is often with more engine mass. Right now, coming to next, and the next classes, what we will be discussing is real nozzle and few more performance parameters of the nozzle to consolidate all of the knowledge that we have learned till now together. Right? With that, I will say thank you. Welcome.
Like, share and subscribe. Hit the bell icon for more updates.